Back in 2017, 8 researchers from Google dropped a paper with a pretty bold title, Attention is All You Need. Now, this wasn't just some small improvement. It introduced a totally new architecture, the Transformer, which has become the literal blueprint for almost all the large language models we see today.
So to really get why this was such a big deal, we have to ask a simple question. What was the main problem holding AI back before this paper came out? You see, the entire field was stuck on a massive computational bottleneck, a problem that was baked right into the DNA of its most popular models.
Before the Transformer, if you were working on language tasks, you were almost certainly using something called a recurrent neural network, or an RNN. Things like LSTMs and GRUs were the state of the art. They were pretty powerful, but they all had one critical feature that was also their biggest weakness.
The paper puts it perfectly. RNNs have an inherently sequential nature. What that means is they have to process information one chunk at a time in order. To understand the fifth word in a sentence, the model had to chug through words 1, 2, 3, and 4 first. It's a step-by-step process, and that creates a massive bottleneck. You just couldn't process an entire sentence all at once.
This table from the paper really just nails the problem down with numbers. Look at the recurrent layer. The number of sequential operations is O of n. That means it scales up directly with the length of the sentence, n. Longer sentence, more steps. It gets slower and slower. But now look at self-attention, O of 1, a constant number of operations. That right there was the key to breaking the whole sequential paradigm.
Now, researchers knew about these limitations, especially when it came to tracking connections between words that were far apart in a text. And their first solution was actually a pretty logical one. They started adding these things called attention mechanisms on top of the RNNs they were already using.
And it was a clever fix. Attention helped a model figure out that, say, a pronoun at the end of a long paragraph was referring to a name way back at the beginning. It definitely improved performance. But, as the paper points out, these mechanisms were almost always just bolted onto a recurrent network. The fundamental problem, that one word at a time processing, was still there. The bottleneck wasn't solved.
And this is where the team behind the paper made their huge conceptual leap. Instead of using attention to just patch up RNNs, they asked a much bigger question. What if attention was all you actually needed? What if you could just get rid of the RNN entirely? This quote from the paper's abstract says it all. Their whole idea was to build an architecture based only on attention. By dispensing with recurrence, they weren't just tweaking the old system, they were tearing it down and starting from scratch, building something designed from the ground up to be massively parallel. Okay, let's just take a look at this thing. This diagram is the heart of the paper. On the left side, you've got the encoder stack. Its job is to read the input sentence and really understand it. On the right, you have the decoder stack, and its job is to generate the output. But the real breakthrough, the reason this changed everything, is what's inside those stacks. They aren't slow, sequential RNNs. They're built from parallel layers of self-attention and feed-forward networks.
So what's the data flow look like? Well, first, the input text goes into the bottom of the encoder, along with some positional info so the model knows the word order. That info flows up through all the encoder layers. The final output from the top of the encoder then gets fed into every single layer of the decoder stack, which then generates the final output, one word at a time.
So what exactly is this mechanism that let them throw out recurrence? The engine driving the whole transformer is something called self-attention. It's how the model figures out the importance of every single word in a sentence relative to every other word in that same sentence. Okay, so at its core, self-attention uses 3 vectors for each word: a query, a key, and a value. The best way to think about it is like a database search. For any given word, its query vector is like asking, hey, to understand what I mean here, which other words in this sentence are the most important? To find the answer, it compares its query against the key vector of every other word. A good match means a word is really relevant. That match score then decides how much of that other word's value, its actual meaning, gets blended into the current word's understanding. And the amazing part, this happens for every single word all at the same time. And this is just a brilliant illustration of how they actually did it. The diagram on the left, that's the basic math, called scale dot product attention. But the real power comes from the diagram on the right, multi-head attention. The model doesn't just do this calculation once. It runs multiple attention calculations in parallel. Think of it like having 8 different experts all reading the same sentence at once. One expert might focus on grammar, another on who did what to whom, and a third on the overall vibe. By combining all those perspectives, the model gets a way richer understanding of the text.
So the model uses this multi-head attention tool in 3 really specific ways.
First, in the encoder, where all the input words can look at all the other input words. Second, in the decoder, where output words can only look at the words that came before them. And third, in the part that connects the two, where every word in the decoder gets to look back at all the words from the original input, which, as you can imagine, is absolutely critical for something like translation.
So, the architecture was elegant, it was theoretically sound, but the real question is, did it actually perform any better? Well, the results were pretty undeniable.
On a standard English to German translation test, the transformer hit a BLEU score of 28.4. Now, BLEU is just a common way to measure translation quality, and that score wasn't just a little better. It beat the previous best models by over 2 full points, which in this world is a massive, massive leap.
And here's the kicker. It was so much faster. The big model hit this new state-of-the-art score after training for just 3.5 days on 8 GPUs. The authors pointed out this was a tiny fraction of the training time for the older, supposedly best models. It was direct proof that their parallel architecture wasn't just a theory, it was incredibly efficient.
This table really puts it all into perspective. You can see the transformer down at the bottom with the highest BLEU score, 28.4. But the really wild part is that training cost column on the right. It got the best results using an order of magnitude less compute. This wasn't just a better model, it was a fundamental change in the economics of training AI. Better results for way less cost.
So the legacy of this paper wasn't just a new high score on some benchmark. It was a total reimagining of how machines process information over time. It kicked off a revolution, and it was all built on the ideas of attention and parallel computing.
And this really sums up the whole shift. The old way, with recurrent networks, was all about processing one by one, which you just can't speed up past a certain point. The new paradigm, with transformers and self-attention, is built to be parallel from the ground up. They didn't just make the sequential bottleneck a little better, they got rid of it entirely.
And this leaves us with the same kind of forward-looking question the paper itself raised. By finding and replacing this one core bottleneck, the transformer unlocked all this incredible progress in language. So it really makes you wonder, what other assumptions are we making in AI that are holding us back? And what other huge breakthroughs are just waiting for another simple, powerful idea like attention?